Hi folks, in 113. Today we're going to be continuing with Chapter 5. Specifically, we'll be doing Section 5.2. Okay. Just in keeping with the usual routine here. Let's look at the calendar. Alright. Today is March 4th. So right on schedule, Section 5.2. One more week before spring break. The packet of material is comprised of these slides. This is a diagram. I want to sort of project this in a moment and then just sort of add details with you. Okay? But this is a good way to think of the various categories, shall we say, of number. You're not responsible for all of it right now, really. Imaginary numbers, not at all. But it exists in comparison, contrast to what we are talking about. So always be aware of the things around you, psychologically, if not physically. We're going to be talking about integers, so I'm going to draw a diagram. This is something I borrowed from my other course that I'm teaching. Again, I'm going to fill this in with you, but this is basically graphing in one dimension, so just horizontally, if you will. Then there's a summary of rules for integers. All right, my observation of people is that even if they know how to add, subtract, multiply, and divide, they do them at the inappropriate times because of the understandable confusion about the conflicting sets of rules that we have. So this is to add some clarity, hopefully, and I'll explain this in detail. Rules that you would apply when you're adding or maybe subtracting versus rules you would apply when maybe you're multiplying or dividing. Right. Then there's comparisons. Right. Some of these are intuitive and some of these are not. The other one not so intuitive. Right. And you'll see why with the number line when I get there. Okay. Then there's exponents. Right. Another operation. An amped up version of multiplication, if you will. Right. Is exponents. Right? It's more specific. Right? It's higher order. Power of whatever the base is. I have to explain to you some details here and here. Right? And lastly, the order of operations you probably are familiar with, right? But mostly they teach you in school these days PEMDAS or GEMS, an acronym. But there's another mnemonic device that I want to show you that I think is better only for the reason that it emphasizes the equal importance of opposite operations. So if you're following along, do please print that, and we'll get rolling here. Okay. Now I may have to stand in the dark a little more than I like. Let me turn on my projector. And hopefully this will cooperate. We did it again, Ziegler. Plug it in, boy. He never remembers. Okay. This is okay. Let us start with the family tree, if you will. I'll explain this. Okay. Now, as I mentioned, there are some things on here that are not really immediately important. The subject for Section 5.2 is realistically the integers, and I'm going to get to that, but there's this other stuff in the way first, right? You are not really responsible for imaginary numbers at all, but I only included, and I mention it now because if you've ever heard the description of something as being real, it might make you scratch your head and go, well, what the hell is that? Well, there's this other category that exists, and that's the perfect example of it. The square root of a negative would be an imaginary number. Right? Anyhow, under the heading of real, there are these two subcategories, if you will. Right? There are things that are rational, including the integers, or things that are irrational. Right? what makes something rational or irrational is basically whether it can be written in the style of a fraction or not. So think of things as rational, even if they don't start out this way. Things that can be a fraction, right, if necessary. Right? Whereas things that are irrational can't be a fraction. No matter what you do, they're never going to be a fraction, right? The reason that they can't be written in the style of a fraction is because things that are irrational are simultaneously these two conditions. They are non-terminating, which means they're infinite, and they're non-repeating, which means they don't have an obvious pattern to them. So if you don't have a pattern, it would be difficult to decide what the actual the numerator and the denominator would be. Right. Famously, pi is an example of an irrational number. All right. We are taught in grammar school, right? It's 3.14, right? But if you have a more sophisticated calculator, it will expose more and more digits of pi. 3.14159 is what I happen to have memorized. It's more useful to that extent, right, in upper level math classes, right, or physics. All right. Anyhow, this might be forthcoming, but it isn't important right now. But it just exists in contrast with what we're doing right now. So worthy of discussion, but not really the objective. All right. Now, things that are rational are things like terminating or repeating decimals. That is, this or that, not at the same time. All right. So, for example, 0.5 5/10, right, is not written in the style of a fraction, but you can convert it to a fraction pretty easily. Its name of its place is its denominator. All right, 5/10 is 5/10, right? Even something like 0.333 forever and ever and ever, right, comes from the fraction 1/3, right? There is a technique that I believe will be discussed in a subsequent section, how to actually start with the decimal and produce this, right, rather than just acknowledging that it started as a fraction to begin with, right? But just beware. Repeaters, that is something that has an obvious pattern somehow, come from fractions, right? And therefore they can be a fraction if need be. Terminating decimals can be written in the style of a fraction. Then there's this other category, right? And again, as I mentioned, this is really the emphasis for today, the integers, all right? Integers are whole numbers. Essentially, with signs, with a plus, a minus, or just being zero, right? The whole numbers, as by definition, are the positives and zero, right? But integers are including the negatives as well, right? All right, so although zero itself doesn't have a sign, any of the whole numbers that are positive are integers. Any of the whole numbers that are negative are integers. And then there's zero itself, the sort of go-between. Right. I made a little mess here, so if you want, maybe I'll just draw this just a tad nicer. Right. Let me move this. Oh, blue is going to be a pain in the neck today, I can tell already. One day the next, it's always different. All right. Integers, think of these categories. Whole numbers, but they could be negative, they could be zero, or they could be positive. That's the most concise way to really describe that. Why not just call them whole numbers? Because integers include the negatives, whereas regular whole numbers do not include the negatives. Okay? And this is our focus for today, these things. All right. Now, to illustrate what they would actually look like or where they would be in relation to zero, let me pull up the next slide, all right, which is this number line. can think of this as being graphing in one dimension, all right? You don't have to do it this way, but it would be best to be consistent. I'm going to put a little mark here every fourth box, all right, to be consistent. This came from graph paper that I drew in like paint or something like that, all right? And it's supposed to be at normal size. That's about an inch, that's an inch, an inch. It doesn't have to be, all right, but I'm gonna make it consistently the same width. All right, this way, and also this way. Okay, the symbols that you see here and here are the infinity symbol, which implies that this stretches beyond forever and ever and ever, in that direction or in this direction. And notice the signs here. This is a negative and this is a positive, all right? For all time, the consensus is that the positives exist from the point of 0 into infinity. This is the realm of the positives, all right? Whereas the negatives exist from the point of 0 backwards into infinity, all right? And since we're talking about integers, right, we're really talking about whole numbers that have a sign and also 0. So here's 0 already placed. I would always include that whenever you draw one of these number lines because it separates out the positives from the negatives immediately. But this would be 1, 2, 3, and 4, say, for example. That's kind of crummy. All right. Hopefully this is a bit darker. Here we go. 1, 2, 3, 4. All right. And on the flip side, well, let me do this first. To distinguish these numerals from their alternate reality here, the negatives, you could, as an option, put a prominent plus sign in front of each of these. All right, so make this +1, +2, +3, +4. All right. It is understood that that's what they are, even if you don't incorporate the symbol, but now watch what happens on the opposite side. It's sort of the mirror image of this, as if 0 were the mirror, all right? So this is 1, but it's -1. This is 2, but it's -2. This is 3, but it's -3. And this is 4, and this is but -4. And it will continue in this fashion into infinity towards the left, right? It is unfortunate, but make sure that you're consistent. When we think negative, associate that with left and with the direction down eventually. And associate positives with right and with up. When you get into graphing in 2 dimensions, it's rigidly going to be this and that, right? Part of the reason, unfortunately, is that the idea of left as being negative somehow is a little bit superstitious. And yes, math should not be superstitious, but it's practical to sort of freeze your mind into a certain perspective. All right, and everybody agrees to the same thing. Kind of like everybody agrees that green means go and red means stop. All right, and if somebody deviates from that, there's going to be an accident. So we're going to stick with this, right? Even if we say left is negative, and that's not really nice in a different context. All right. All right. 0, as you can see, is still here. And it is neither here nor there, right? It is neither positive nor negative, right? Everything is in relation to this. 0 is what you might call a reference point, right? It's a frame of reference in which other things are compared to it. Other things compared to it. Right. How far away is the number +2 from 0? It's this magnitude. Right. Magnitude is a word that you will hear a lot. It gets thrown around a lot. All it means is basically distance from 0. Right. That reference. All right. What is the magnitude of 0 to -2? It's the same magnitude but it is opposite direction. Okay? So two things, a negative and a positive 2, can have the same magnitude. That's how far away from 0 they each are, but the sign denotes which direction they are in relation to 0. Negative 2 is left of it, positive 2 is right of it. Right? Just beware of that word, magnitude, because it is technically what you should say rather than what we often say, which is the size of the number. All right? It summarizes that. I mean, it's slightly less verbose, right? Size of the number versus magnitude is maybe the same. Well, I don't know if how many syllables that is. Magnitude, 3 syllables, right? The size of the number is 5 or 6 syllables. All right, so slightly less efficient. Okay. Okay. Now what? Let me turn my own page here and see what's next thing. All right. Let me give you some comparisons, symbols to work with, which is indeed another slide here, and then we'll do some actual examples. So I got to move this from here to here. All right. I posted this in a different arrangement. Okay. All right. This is a summary. When you're trying to compare two numbers in terms of which is less than which or which is greater than which, remember, first of all, we have these symbols to work with. We have the less than symbol. I'm going to put it up here. If it's oriented like this, the point facing towards the left, this is referred to as less than in English, right? If it is oriented like this instead, then this would be referred to as greater than, at least in English. That's how you would say it. Right? And that's really all that is important to us right now. In theory, there are other symbols like less than or equal to, and there's greater than or equal to. But it's really these two that are more important right now. All right. You could be talking about the same two numbers from different perspectives. Here's an example. I think everybody would take it for granted that the number 2 is less than 3, right? But if I refer to things from the perspective of 3 first, this would be the appropriate way to talk about it, all right? Notice where the point is. The point is facing the smaller thing, all right? And in this instance, that point is still facing the smaller thing. It's kind of like talking about the same subject using different words, and it'd still be correct. Like, for instance, you can say, I'm staying home, which means what without using the words? It means you're not going out, right? This is an alternative way of talking about this scenario, right? Just read it correctly if it's aimed like that or that alternatively, right? Now, as a rule, because it is maybe slightly counterintuitive when we're kind of conditioned to think about things in terms of magnitudes, right? As a rule, the positive thing, if you see a positive sign, or even if it doesn't have one, then you would assume it's positive, they're always going to be greater, right? Regardless of their magnitude, than the negatives, okay? Automatically, all right? You'll see some examples in a moment. If you are comparing two negatives at the same time, all right? This is how you decide what the relationship is. The negatives that are somewhat ironically closer to 0 are always going to be greater than the negatives that are farther from 0. That means these are going to have larger magnitude, meaning their distance from 0 is going to be greater. All right? But nonetheless, this is going to have smaller magnitude. And for that reason, it might seem counterintuitive to us, right? Which is why I'm mentioning it. But convince yourself that this is truth, all right? Negatives closer to 0, they're closer to the positives, right? All right, as well, are always going to be greater than the negatives that are farther from 0, in spite of the magnitudes, right? In spite of the size of the numbers. Okay? Now let's do some examples, all right? And I will try to maybe do them here without turning off the projector just yet. I need the space. Maybe I'll scoot this down ever so slightly. All right, and at the same time, pull up this this number line just temporarily, so I can toggle back and forth here. All right. Now, let us say for an example, we'll do several, right? The duds. I'll put that aside. I'll do up here 4 examples. All right, to get us rolling here. And I'm going to purposely use similar looking digits in some instances. All right, so we just did this, right? 3 is what relationship to 5? All right, because we have it brainwashed into our minds since a little kid, that's a bigger number, right? What we really should be saying now that we're older is that that's a larger magnitude. Its distance from 0 is greater, right? And since we're dealing with 2 positives, it's really not an issue to us. So we would say that from the perspective of 3 on the left, 3 is less than 5. That would be how you would compare those 2 things. What if, on the other hand, you had this situation? Or alternatively, you had 3 compared to negative 5. All right? We're comparing 2 negatives at this point. All right? Well, if you look at a number line, and I'll just scoot this down for a moment. I'm going to make this a little bit smaller just so it fits. 1, 2, 3. Negative 3 would be located here in relation to 0. And negative 5 would be located here in relation to 0, its reference point. Which one is further away? Right? This is farther. Right? This is closer to 0. Right? So according to our established rules, even though magnitude is probably driving us all nuts at this point, when comparing 2 negatives, the negatives closer to 0 are understood as being actually greater. This is the relationship. Right? It's counterintuitive if you are just grasping the concept of size and not direction. Right? You don't have to draw a number line every time as long as you memorize these 2 relationships. Right? This is a smaller magnitude than this, but this is closer to the positives. So by default, this is greater than that. Right? It's not as severe, right, if you will. If you had this scenario, negative 2.8, a decimal number, compared to another negative 2.7. This one is a little bit trickier because you're dealing with decimals at this point, all right? But the relationship is still true. All right? The negatives closer to 0 are greater than the negatives farther from 0. All right? Question is, when you're looking at 2.8 and 2.7, which is actually closer to 0? if I drew this on a number line, the 0.8 and the 0.7 would be a tenth, 7 tenths and 8 tenths. Right? I don't think I could actually fit it on this line here, but let me sort of try to get the point across here. I'm going to count 5 spaces. 1, 2, 3, 4, 5, just to get an estimate here. 2, 3, 4, 5. All right, here's -3. Here's -2. That's -1. -2.8 and -2.7. -2.8 is a larger magnitude, which means that it would be approximately here. All right, it would be slightly closer to -3, because the next number after 8 is 9, and then the next number after that would be 10, which would make this 2 increase by 1. That means that 2.7 would be just ever so slightly in front of it. It would be about behind it here, technically. All right. 2.7 is here, and 2.8 is closer to 3. All right. So, which one is closer to the 0, though? Which one is closer to the positives? All right. The 2.7. Right. Therefore, this is the relationship from the perspective of 2.8 written on the left side of the symbol. -2.8 is automatically less than -2.7. If we were comparing these things at the, like one of each, let's just say that you had a -4 compared to a +3, right? What's the relationship in that case? All right. The positives are automatically greater than the negatives, which is, again, probably counterintuitive to us, because from a little kid, we have been conditioned, brainwashed, all right, basically to go, look at the size of the digit. The magnitude is what we're calling it now. And we would say 4 is a bigger number than 3, right? If they would both be positives, that would be a fair comparison. But the reality is that we have one of each in this case. We have a positive number and we have a negative number. So the relationship would be this. -4 is less than +3. Okay? Now let me do one other thing I'll show you. I may require me to turn on the light here for a moment. All right. What about when you're dealing with fractions? All right. Here's another example. I'll just put it here underneath it. When you're comparing two fractions, there's a shortcut. That always works. Right? Basically, the shortcut is this. Cross multiply and compare products. Instead. Okay? So, for example, if you had, I'll put it over here, -4/7, and you were comparing it to -3/5. Okay. I want to establish this. Is this less? Is that greater? It's not so obvious, right, when you have fractions, because in theory, you would have to upgrade these to something with a common denominator. And once you've changed the denominator, you would be obligated to alter the numerators in a similar way. Anyhow, we haven't really gotten to that subject yet. You may be aware of it from your earlier education, but here's what you do, all right? Just pay attention to the numbers for a moment, all right? What is 3 times 7? Oh, 7 times 3. 21. This thing was a negative to begin with, so I'm just going to tack it here. All right. What is 4 times 5? Just pay attention to the digits again. All right. This is 20. All right. This is standing in place of this negative here, so I'm just going to tack it here. So basically what we're doing is we are comparing the product of negative 20 and negative 21. Negative because the fraction was negative to begin with, and negative because this fraction was negative to begin with, right? So compare negative 20 to negative 21, right? This is a little bit of too much scribble now, right? So I'll turn off the light for a moment, all right? The negatives that are closer to 0 are automatically greater, even if that defies the usual logic of we look at the magnitudes, the size of the numbers, right? Negative 20 would be ever so slightly closer to 20. Negative 20 would be slightly closer to 0, I should say. All right? So therefore, from the perspective of 20, this is the relationship, greater. Negative 20 is automatically greater than negative 21 because this is closer to the positives. And the positives are always greater, all right, than negatives. So since it came from the fraction immediately underneath it, they have the same relationship here. Negative 4/7 would be greater than negative 3/5. Right? You could make this a decimal if you wanted to, as an alternative. The decimals are not exactly a cakewalk either, so it's up to you. All right? I don't want to talk you out of it one way or the other, but I think the shortcut is more efficient. All right? 4/7 would be approximately 0.57, and 3/5 would be exactly 0.6. All right? So if this is negative and this is negative, 0.57 is just shy of 0.6, which means that, again, this would still be closer to 0 and the positives. So this would still be the same relationship. All right. All right. I just divided the top by the bottom to get that figured. I rounded it. All right. Now, let's see. I have to turn off the projector for a moment because I got to draw you a diagram. And Dracula will have a little bit of light now. Whoa. All right. And, ooh, it's a nice day. Nice light. We'll switch gears here for a moment. Yesterday. I'm going to stick with black just because it's a little bit more conducive. All right. There's some alternative ways you can write signs. Okay. This is considering when there's a plus or a minus sign or signs between numbers. Right? Just remember this is alternatives. Sometimes it's to your advantage to look at something from one perspective rather than another, but one is not better than the other. It's just their options. It depends on the situation. All right. There's this situation where you have, let's just call it a double negative. All right. Here's what I mean literally. You have a nondescript number here and a number here. And in between them, you see a double negative, like that, right? Even if it's encapsulated into parentheses, never mind that. As an alternative way of writing it, and it might be to your advantage to do that, you can do this. Group these together as just one big plus. Okay? If something happens to have no sign here to begin with, right, you could always fill that in as well, right? You could just assume that it is a positive, this thing adjacent. If, on the other hand, you have the situation where you have a single minus sign, between numbers, right, it would look like this literally. You would have some number and then some other number, and there would be this minus here like so. If it is a convenience to you, you can write it like this instead. You could write it as specifically plus a negative, like that. And I will put a little heart shape around this because it's kind of heart shaped. Love. Okay. The plus would be more prominent usually, or if there's a parentheses involved, it would be outside. Okay? That's the way you should write that. If you're going to use this option, plus this minus in between, you could write as a big plus and a slightly smaller negative next to it. Smaller only to make it seem less important, even though it is important. Right? You would attach that sign of negative to whatever is still sitting here, right? And there is that, all right? Again, if there is no sign attached to something here, then just assume it is a positive, okay? Now, let me get into this discussion. I definitely have to turn the projector back on now, and then we'll do some examples. I've often told people this. I finally made a handout which I hope is useful. Right? If there's a reason that a kid or an adult, right, anyone, a math person of any sort, right, makes a mistake when it comes to a solution, it's probably because of some sign issue. Right? Confusing one set of rules with another. That's my observation. All right. So to summarize, here's what I've come up with. All right. As far as an infographic. All right. We know that we have signs that are positive and negative. All right. There's a set of rules for when you're adding and subtracting. All right. To realize something. It is the combination that decides the operation. All right. So if you have the same set of signs, you're actually going to add. And if you have one of each sign, then you're actually going to subtract. Once you convince yourself of that, you will strategically write the problem given to you in a way that allows you to use these rules, right? What I just mentioned before, that a double negative between could be written as a positive, that's still true, all right? And a single minus between can be written as plus a negative, all right? 0 is neither positive nor negative. That's all still true. The real important thing to convince yourself is this. Combinations decide the operation insofar as adding and subtracting are concerned. So if you're having trouble deciding which is actually going on, check to see if you have the same or one of each. You're always comparing two at once. All right? When you get to the rules for multiplying and dividing, on the other hand, they're different. All right? And usually it's more obvious whether you're dividing or whether you're multiplying. There are some reasons that you might confuse them. All right? We're used to seeing, say, for example, a multiplication x. In upper level math, they switch at some point to a dot, and then they don't use anything at all. They just might butt things together in parentheses. All right? Those are options for multiplication. All right? For division, in the United States, we're taught that the most basic symbol for us is the colon with the line through it. I've seen elsewhere, and this is still fine, just a colon, right? Or there's the forward slash, or there's the box, or there's the box oriented this way, or there's just something on top of something else. All of these symbols imply dividing somehow, right? These are the symbols we have to imply multiplication. Anyhow, the sign combinations do not dictate the operation when you're multiplying or dividing. The only thing that the sign combinations decide are the sign of the answer, which is good news. It means that for the most part, if you start out multiplying, you're going to continue multiplying. And if you start out dividing, you're going to continue dividing. The only exception would come eventually when you divide by a fraction, but that's the future. And that is for a different reason. All right? It's pretty much straightforward. Multiplying is multiplying, no debating. Dividing is dividing. But the answer, the product in some cases and the quotient in others, would be a positive when they're the same signs. A negative times a negative is a positive. When you have one of each sign, one thing is positive, one thing is negative, the answer is negative. Okay? So if you feel a little rusty, all right, or you're a little suspicious of your calculator perhaps, all right, have this reference because it's true, all right? And then eventually the more problems you do, it will start to sort of burrow into your brain. You won't even think about it twice, right? It will become second nature. All right, let's do some examples. Let me turn this off again. Light, is this light a little benefit? Maybe a little bit. I don't like the glare. I can't unfortunately move my lamp up any further because it's up against the ceiling. So maybe I'll just leave it off. As long as it's visible. My shadow is not complicating things. Me and my shadow. Alright, here's some examples. Let's see. 1, 2, 3, 4, 5, 6, 7, approximately. So let me draw a little scaffold for myself here. And I'll try to work things in like this. I'm working with a landscape orientation now, rather than a notebook is more portrait style, right? So I have to compensate by making these little borders for my own sake. So let's consider this problem. -5 plus -3. If you just, to this point, I have not really encapsulated negative integers in a parentheses like so. It's kind of an over explanation. A textbook has a tendency, and I can't help but sense the reason is because of being stuck in a frame of mind, right? I don't really want to belabor the point, but let me tell you something really quickly. We have computers that have a QWERTY keyboard, right? I'll show you mine, right? I'll still unplug this. Here's the QWERTY keyboard, right? On a computer. Why do we have that? The QWERTY keyboard was invented like something like 150 years ago, all right? It was invented to resolve a mechanical issue, all right? If anyone has ever told you, oh, well, the letters are arranged on a keyboard to make you type faster, that's not exactly true, all right? They may have strategically, per se, put the vowels in a certain arrangement, but the computer equivalent in the 1800s was a typewriter, which was mechanical, right? So what would happen is that people when the keyboard was originally in alphabetical order, you know, it becomes so predictable and so familiar to people that they would press a key and then press another key rather quickly. And in the process, right, the keys would bind because they were on little levers, right? The certain keys that ended up getting pressed relatively close to one another would get stuck, all right? So the QWERTY keyboard was invented to basically make it less likely that the things that get pressed a lot are adjacent, all right? Anyhow, computers are no longer mechanical, all right? And you might be scratching your head and going, why are you telling me this crap for, right? Humor me, all right? That's an example of where we continue to use something, the QWERTY keyboard, because we're kind of just used to it. Not for any real reason anymore, because nothing is mechanical anymore. Computers are electronic, right? The signal is an electronic signal. There's no mechanism that's doing this to type, all right? Another example of where we are basically kind of set in our ways is this, right? I don't know for a fact, all right? But I would guess that textbooks have a tendency to write things with the parentheses, because if you were using a typewriter, all right, it would be a little bit more difficult to make things in superscript, all right? What I'm getting at is that this is evidence of us continuing to do something because of a difficulty in writing that way, all right? You can write in superscript and subscript pretty easily using Microsoft Word or Google or whatever have you now, all right? But textbook publishers are borrowing something that they've been using a long time, all right? They don't use typewriters anymore either, all right? But that standard of, well, this is easier than rolling the paper to make something a little bit higher or even a little bit smaller, you know? Anyhow, I guess I'm going off at a tangent, so I'll stop. What I'm getting at is this. You can now change this to conform to this set of rules, right? Or, and I'll give you yet another alternative if you prefer it, all right? I'm going to use these rules, and I'm going to show you something else that also works to get to a problem like this without a calculator, all right? This is an example of basically that situation from before, when you had a single minus written like that, right? The heart shape, remember? Single minus, but rather than starting with this and converting it to that, you could put it like this, -3, all right? And therefore, when you're considering the signs, now there's the issue of what, all right? Are they both the same signs? Or are they one of each? Because that will decide whether you're really going to add these or subtract these. From this perspective, these are same signs, which means, somewhat ironically perhaps, what are you going to do? You're going to add. All right? What's 5 plus 3? 8, right? Is the actual magnitude that would be the answer as a result, right? What is the sign going to be of this? This little subtype here that I wrote, and I'll read it to you now. The answer, regardless of this scenario or this one, is always matching the sign of the larger magnitude, right? In this case, it's kind of irrelevant because in this style of writing them, they're both negative, all right? But if we stick with that logic, it's always going to match the bigger digit, the larger magnitude. What is the sign of the larger digit already? Negative. So therefore, this is negative, all right? As an alternative, if you don't like that, all right, or you feel a little unsure about it, there's one little thing that you could say to yourself that will work just as well, right? And I'll put it here. A negative plus a negative is a positive. Pardon, that's when you multiply. Is a bigger negative. A negative plus, that's this. A negative plus a negative is a bigger negative, right? I kind of jumped the gun and I said this other thing too, so I'll put this over here as something of an afterthought. A negative times a negative is a positive, right? That's something that you have to separate out in your brain because that's multiplication. But if you know that you're either adding or maybe subtracting, you can't decide between those two, convince yourself of this alternatively. A negative plus a negative is equal to a bigger negative. Bigger magnitude would be a better way of saying it, larger magnitude. Anyhow, that's one perspective that will accomplish this, all right? This is, to me, the better one, really, in the long run, all right? You just have to realize that you could toggle between writing something this way, between numbers, number, and writing things this way, All right? This is more or less what was given to you to begin with, and this is what I turned it back into. Okay? The hard part is deciding ultimately, am I adding really or am I subtracting really? The combinations are going to dictate that. All right. Here's a similar looking problem that I'll put here. All right. If you had -4, and I'm going to stick with old-fashioned typewriter way of writing this because it still exists, just as we're used to using a QWERTY keyboard, but you know, writing something this way rather than having this in a superscript, all right, a little bit smaller font, a little bit higher up, is just being set in your ways and not really paying attention to why, all right? When you had typewriters, you used to have to roll the paper up strategically to get it to write in a different location, all right? So that's kind of a nuisance, and the way around that was to encapsulate the negative. All right. Anyhow, what do you have in this situation? You have essentially a number with two negatives in between another number. I'm looking at these two here. Yeah, I know there's a parenthesis here. Forgive it for that moment. What is a double negative? A positive. So this is really +3 sitting next to -4. And the reason why I would take the time to look at it from that perspective is because then you could apply these rules as they exist, which dictate that if you have one of each sign, as you realistically have in this case, what are you actually going to do? Are you really going to add, or are you going to really subtract? One of each says subtract. All right? What's 4 minus 3? All right? Insofar as the digit is concerned, it's equal to 1, all right? What is the sign of the answer going to be? The sign of the answer is automatically going to be, it's going to match the bigger digit. Bigger magnitude is the word that I'm obligated to say. The bigger magnitude is 4. It's further from 0. What is its sign? Negative. So what does this have to be as an outcome? It has to be negative also. All right? You could verify this with a calculator. Granted, you have calculators, right? And your calculator has a little button on it for suggesting that something is a negative. You could use that. No sin in that. But still, don't absolve yourself from the responsibility of memorizing some rules, because it will make you more strategic, right? The calculator can't be strategic for you. Okay? So, first problem, -5 plus -3 is -8. Second problem, this is kind of the worst case scenario where you see nothing but minuses, all right? And this is the operation you actually do, subtraction, all right? -4 is really +3, all right? And therefore, one of each sign, you're really going to subtract to get 1, and it is a negative because of the larger magnitude, all right? This is negative because of the larger magnitude, and it works 100% of the time. Okay, now, let's do some more. When we get into multi-operational problems, something that involves several operations at once, you're hopefully better. A person is hopefully better at that point, more comfortable with sign changes, because it will be maybe adding and subtracting rules and multiplying and dividing rules simultaneously. All right, here's the next example. All right, here is 15 minus 20. Okay. Now, what I would do to sort of dress this up, only for the sake of applying the rules that are established, is this, all right? Fill in some missing information, all right? What is the sign here that is not written? What would you assume it is? It's actually positive 15. And therefore, we don't really have to tweak this. We could just leave it as it is. Negative 20, all right? So what does that mean really? It means that we have one of each again, we always associate the sign with the number that is immediately adjacent on the right side. One of each sign. So therefore, what are we actually going to do? We're going to subtract. What is 20 minus 15? 5 is the digit, right? What is the sign going to be of 5, right? Negative, because it matches the larger magnitude. So it's negative. Okay? Is a multiplication problem, finally. You know what, let me do another, one more subtraction problem, because those are arguably the harder to decide. So if you had 40, all right, minus, again, the old-fashioned way of writing it, encapsulating it, all right, what is going on here again is writing this way rather than that way. Superscript, because you would have to move the typewriter paper, all right, in order to write that. All right. What do you have here? You have a double negative in between numbers, which means that this is really a plus 8. All right. What again is the sign that is attached to this 40 that's not written there? All right. It's really plus 40. All right. It's implied, for better or for worse. Right? Math people are notoriously lazy, which is another way of saying efficient when it's convenient for them. They leave out ones, they leave out zeros, they leave out decimal points, and they leave out positive signs. Right? And then when we get into, if you ever see radicals, square root stuff, they leave out the index too. Right? Because it is understood, it is implied somehow. As for the rest of us novices, right, that's kind of inconvenient because you didn't explain something. I say, especially when you're dealing with little kids, over-explain. Always show multiple paths to the same destination, right? Not one thing in lieu of another, all, right? What is the nature of these two? Are they the same signs or are they one of each? In reality, they're the same signs. So if they're the same signs, that means you're actually going to add. This is the ultimate example because if you saw this as a person who has never seen integers before, what would your guess have been in terms of what you're supposed to do? You would go like, well, there's nothing but minuses there. So that's twice as much subtraction, right? No, all right? A double negative between numbers, never mind this squiggle here, all right, is a positive, all right? That's essentially multiplying without really consciously thinking about it. Anyhow, that makes that really positive 8. This doesn't have a sign attached to it. One would assume that it's positive. Have to, all right? So at that point, when you have it cleaned up, just one sign next to one sign, you decide, are they the same or are they one of each? They're the same in this situation, actually, so therefore you really add. What's the digit going to be? 48, all right? Because 40 plus 8 is 48. What is the sign going to be? So it's going to match the bigger magnitude no matter what. The answer is positive 48. Okay? Now, let's do some multiplication examples and some division examples. Yes, my computer fell asleep again. Okay, man, wake up. Beware, again, when you're dealing with multiplication, you might see something in the more intuitive fashion, say using an obvious multiplication x, all right? Or you might see a dot. That's a 3, I swear. So just a 3 with flair, all right? Or you might just see simply two things butted up against one another like this. These are all multiplication, right? In another situation, they could, in theory, put another parentheses here. If there is no symbol in between these parentheses, it is still implying exactly this. All right, multiplication, multiplication. All right. Anyhow, we don't have to worry about whether we're multiplying or not, because again, the multiplication division set of rules just merely dictate the sign of the answer. So, what's the digit going to be? 2 times 3 in any situation is 6, right? What is the sign of the answer going to be? All right. This is really a positive again. It's not written. So it's positive, positive. That makes this one of each, right? Which means what? That's a C, right? One of each sign means that you're going to get a negative answer. It's a negative 6. Okay? Here's another one. Negative 7 times negative 8. Depending upon who's writing it, they might put a dot here or not. That's kind of overstating the case. If you just see 2 parentheses butted up against one another, no plus, no minus in between them, it's understood that this is multiplication. This is really that, all right? So, establish the digit first. 7 times 8 is 56. What do we have here? Same signs. So that means that the answer is going to be this scenario. Negative times a negative is positive. Positive 56. Okay? One more. All right. A division problem. I'll put it here. The tendency in algebra, at least, is to write things not so much using this colon symbol, but more the sort of fraction-esque way of writing division. You know, that obvious line between a top number and a bottom number. All right. So if you see something like this, all right, or even still, a negative out in front, all right, it means 63 divided by 9 really. Right? And you could write it like that if you want to. You could put 63 here and 9 here. You would be obligated to put 63 on the left because division is not commutative, all right? Nor is subtraction. The only things that are commutative are adding or multiplying, all right? Order matters when you divide. What is on the left goes on the top. Right? So this would be 63 on top, 9 there, all right? You could do that if you want to just establish, firstly, you know, what the number is, the quotient. What is actually 63 divided by 9? It's 7, right? Now, insofar as the answer is concerned, right? If you see something, and textbooks do this a lot too, they don't really favor attaching a negative sign to either the top or the bottom, but I would, as a habit for your own sake, automatically associate this with the top. All right, it will spare you a lot of trouble. And what that would mean then is that this is really negative 63 sitting on top of 9. But what would the sign of 9 have to be at that point? It would have to be positive, really. The only reason I would belabor this point, again, is to apply the rules. Do you have one of each, or do you have both the same signs in this case? It's actually one of each, which means that the answer is going to be negative 7. Okay? So beware of that. All right, now let me turn on my projector again, and I gotta show you exponents. Take a look at this handout. I made it purposely blank in 4 places because I want to write something to talk about it. The act of writing, it may seem silly, like why don't you just type that? When you're teaching, you have to look for little teeny tiny exercises like this, bite-sized little projects. Not to, you know, give something busy work. right? It's because when you physically write something, all right, you are using more of your brain than just simply typing it, right? The act of physically writing requires a greater degree of sophistication, actually, neurologically, than simply typing something, right? You could type very quickly, right? But if you wanted to make something legible, you have to scrutinize it a little bit more closely, right? Anyhow, in the process of physically writing something, you're more inclined to remember it. So make little things like this for your students to, they don't take very long, right? But get them to sit down and focus, all right? Walk them through the process, all right? Anyhow, you may have heard of the phrase powers. You may have heard of exponents. Now, just realize this. There's the individual parts involved, right? And when you're dealing with exponents, let's just say this up front. Exponents is a more sophisticated form of multiplication. Right? There's the opposite of exponents, which is roots. You may have heard of square roots and things like that. Think of exponents, little digit here, as being an amped up version of multiplication, and think of things like roots or radicals as being kind of an amped up version of division. Right? They're more specific as to what you have to do. Right? Anyhow, the individual parts are as follows. The evidently larger thing that should be written on the bottom, normal levels, normal font size really, is called the base. Right? The thing that is written in superscript, so a slightly smaller font and a little bit higher, all right? That is the actual exponent, and that's really the instruction, right? Now, as for this phrase in English, because English can be confusing, and often it is, as a math teacher, it gets you in trouble, beware, all right? A power of what's going on in this thought cloud here, it's a power of. The whole thing is a power of whatever the base is. What's the base? The base is 2. So this is how you would say it precisely. All right? All right? This is a power of 2. Which specific power of 2? It is 2 to the third power. That's how you should say it if you want to be very explicit about it. You could roll the R, all right, with amazing facility, right? Makes math very, sexy math, right? Not good for math, really. Math is so asexual, and it should be. But to get people's attention, all right? Hey, babe, check this out. 2 to the third power, all right? Here again, English gets you in trouble. There's the number 2, and then there's 2, the place you're going, right? All right, which is not to even mention 200. T-O-O, 2 is an also. All right, homonyms, all right? Anyhow, this is as you should say this particular example, all right? Let me erase some of the gobbledygook here because I don't want it to be distracting, all right? This is a power of 2, specifically. It is the third power of 2. Now, here's what people say in ordinary conversation, and it's one of those things that we all know what you mean when you're saying it, but you shouldn't say it that way, right? Now, the analogy I have, and I'm just grasping at straws here, is when you're a little kid and you get caught playing matches like me, all right, and your grandma goes, "What are you doing?" All right, you say, "I ain't done nothing, Grandma." All right, that's not, really a sophisticated way of speaking to begin with, right? But if you analyze the words ain't and nothing, right, it's really a confession without really meaning to confess yourself. To say, I haven't done anything is to say, I'm not guilty, right? But to say, I ain't done nothing, technically means you have done something, all right? And when you say that in ordinary conversation, everybody knows what you mean. You're not trying to express guilt, culpability. You're not confessing yourself, all right? But you're being imprecise, all right? Anyhow, math, you have to be precise, right? And you need to teach and encourage precision, right? So here's what people will say, erroneously. They will say this: 2 to the power of 3. That's not correct, all right? Why is this wrong technically? All right, not to, don't beat somebody to death when they do this, right? I've seen newscasters, say it this way. 2 to the power of 3 is wrong because what is it actually a power of? It's a power of that, not this. Right? Third power is the precise way to say it, right? In English at least, right? Again, English is confusing, all right? Not power of 3. Don't say that, right? All right. So, no, don't do this, all right? Yes, this is cool, all right? Sunglasses, all right? Look how large that happy sun is. There we go. 2 scoops of raisins, okay. All right, now what is the actual instruction? All right, the actual instruction is this. As I mentioned, it's a slightly more sophisticated form of multiplication. So just to get this out of here, and having said that twice now, all right, here's what the instruction is. In the least obvious incarnation of the instruction, what you are expected to do is this, all right? You're to write, in this case, 3 iterations of 2 and then multiply. That's what you have to say first, right? Because it's so alien, the word iteration, to a kid who's, like 10 or a little bit younger. They will not really know what you mean, and therefore they will not confuse it immediately with something else because it is new, right? It's a novelty, the word iterations, usually at that age, all right? Write 3 iterations of 2 and then multiply, all right? In a more plainer way of speaking, and I would do this for sure, what does that really mean? It means write 2 3 times and then multiply. All right, hopefully that's not too dark or off the screen here. I'll put the curtain back just to read this. All right? Writing 3 iterations of 2 and then multiplying is literally writing 2 3 times and then multiplying. All right? It means literally doing this. Writing the number 2 thrice, all right, and then multiplying. What is 2 times 2 times 2? 8 is the actual simplified equivalent of this, all right? Here's what, once you have said this though, what it is written in black, here's the mistake that people always make, all right? Little kids especially, right? They go, oh, because English gets you in trouble. All right, as a math teacher, all right, write 2 times 3 and then multiply. Now, the same words are being used, right? Write 2 times, and then there's the word spelled out for 3, and then multiply. Write 2 times 3 and then multiply. They're the same exact words in a different arrangement, right? You have to be precise, right? And you have to encourage and teach precision to a little kid. It's very important insofar as mathematics is concerned. When it comes to something that is more an expression of one's feelings, all right, precision would be great in the long run, but you don't have to start out that way, Like if you're making a painting, sometimes the blurriness of the painting is kind of autistic in and of itself, right? And we could appreciate it for that, like a Monet painting, I believe, right? Right? It's a little bit more unclear, literally. Don't go to sleep. Okay, so What's the problem? This word and this word are in different positions. And doing that does not mean the same thing, right? In this context, the word times is meaning to say you physically write 3 iterations of that number 2, right? That's a verbose way of saying it, right? The context is you write something repeatedly, right? The context here is more literal to that symbol, all right? And so what happens is that you have a kid do, all right, you want me to write 2 times 3. It involves multiplication, and they already think that they're ahead of the game, right? And so then they do, well, it's 2 times 3. You get 6, right? What compounds the issue is that the first example that usually is given to them is one that really you can get away with it thinking about it either way. 2 times 2, right? It's just 4, whether you say it one way or another. That's the only time that works, though. Anyhow, 8 is not equal to 6, all right? Which one of these is correct? This one, all right? Do this. Don't do this, all right? And make sure that your kids, when you're telling them for the first time, all right, that they have to be careful, all right? English is confusing. Why? Because there is room for ambiguity, which is great when you're trying to write poetry or something like that. I don't really want to, demean it at all right, or denigrate it, all right? But when we're teaching the subject of math, we have to teach them to think very linearly, very precisely. All right. Now here's some examples. And again, I'll turn off the projector and give you some examples that involve an exponent somehow. Okay. I'm going to just draw a little border here like this. Oh, we have time, an hour 17. Okay. Suppose, as an example, you were given this. -5 purposely written into a parentheses, and then the exponent is on the outside, all right? Which is going to be contrasted with something, almost the same thing, but no parentheses, right? The point of this conversation is simply this, all right? Parentheses is right, are important. They're basically like putting blinders on, right? They're trying to narrow your peripheral vision to just pay attention to something very specifically. It's a way of drawing attention to something, right? So if you see parentheses intentionally written, right, whether you put them there or the textbook or what have you gave it to you, just realize that it's going to be a different answer ultimately in a situation like this. Okay, now here's what would happen. If we follow the instructions rigidly as we should, all right, in math world, all right, this being encapsulated as it is suggesting that both the digit and the sign are affected by 2. Right? In a situation like this, what is being stated here, very subtly, right, is that only the digit is affected by 2. The operation being an exponent, an amped up version of multiplication, slightly more complicated. Right, so what I do is a lot of times I will draw little arrows to sort of give myself visual cues as to what I have to do. All right, this 2 is affecting both this and this. All right, that's what this is saying verbally. All right, this is a little bit more nonverbal. All right, in a situation like this, it's just the 5 that's being affected. All right, So if that's the case, we're going to replicate -5 twice. And if you want to write it like that, go ahead. All right? It's really -5 times -5. That's the instruction. Write 2 iterations of this number. -5, -5. There's 2 of them. In other words, write the number -5 twice. All right? Then multiply. What is 5 times 5? 25. Sign combinations, though. Same signs is a positive. So it's positive 25. All right? And there ultimately will be the difference. All right? In this instance, it's saying write the number 5 twice. 5, I'll put this in red. All right? 5 times 5. All right? Which again is 25. But then the thing that was unaffected didn't just go away. It's attached as an afterthought. Okay. That negative has to go somewhere, right? Tack it on afterwards. Okay? I don't think you're responsible for the thing I'm going to show you, but it's still practical anyway, so I'm going to give it to you. Imagine we'll do an example of each of these, and then we'll sort of contrive a rule to spare you some trouble in the future. All right, let's take something deceptively easy. All right, suppose that you had this, -1 encapsulated, and it was an even, right, nondescript number here, versus the situation when also encapsulated -1, but it's an odd number, an odd exponent. All right. Let's think of the easiest example of each of these, because that will basically help us contrive a rule. All right. As an example, -1 squared. The instruction is to replicate this as 2 iterations of -1 multiplied. All right. 1 times 1 is 1. That's super easy on purpose. Right? A negative times a negative is a positive. Same signs, positive when you multiply. Okay? Or divide in theory. What about the easiest example we can think of this? Not using 1 would technically be the easiest, but how about 3? Because it would be a little bit easier to remember. -3 here. All right? This would say, write 3 iterations of that. Clone this. -1, -1, -1, times. All right, and if it makes it more obvious that these are distinct factors, I'm going to encapsulate them each. All right. Those extra parentheses is not really necessary except for the sake of clarity. All right. So you have that option. Maybe if I put this in a different color, it'd be a little bit more obvious that this is multiplication. All right. Now, work left to right. Do these two first. -1 times -1, we've already established, is +1. What is this times the leftover -1 here? -1 times +1, one of each sign, means that this is going to be still 1 for the digit magnitude, all right? But when it comes to one of each sign, right, one of each sign when you multiply or divide is a negative answer. All right, so this is going to be -1, all right, versus a +1. When you have this situation, maybe for reference later, convince yourself of this. As long as this is encapsulated like it is, all right, you're going to get a negative answer. Pardon me, a positive answer. I'm not even taking my own advice. Guaranteed, whatever the magnitude is. All right. In this scenario, when you have an odd, you're going to have a negative outcome, a negative answer. Now you might wonder to yourself, well, geez, that's really unnecessary. I could just go through the mechanics of this and you get to the answer. That's true. All right, it is true. All right, but it would become more and more of a chore. All right, the larger the exponent. So say, for example, you had this now. Suppose that you had -1 to the 57th power. Yeah, that's right. That's correct pronouncing it. 57th power of 1, -1. You can, if you want to, make 57 clones, if you will, of -1. But it's going to be a nuisance, right? To have to go there, -1 times -1 times -1 times -1 times you could do it brute force. Brute force works, but it is very tedious. All right, and yeah, there's ways around that, but if you memorize this relationship, you'll spare yourself a lot of trouble. All right? If it's just 1, what are you guaranteed as a digit anyway? 1 times itself is going to be 1, no matter how many times or no matter how many clones involved here. All right? If you have an odd, all right, you can predict that the answer is going to be negative without going through this. Okay? All right, so odds are negative and evens are positive. All right, here's the last thing before the last 2 examples. The order of operations, which again, you probably have some familiarity with that. I would bet you have familiarity with that. But I want to just, I would be remiss if I didn't talk about it. So let me make sure it's clear. Come on, wake up. There we go. All right, so this slide, the last one here. There you go. All right. The order of operations is a list of things, things you must do in a particular order. All right. Operations being adding, subtracting, multiplying, or dividing is just a couple of examples, 4 examples. All right. But the problem is that we have to have a consensus as to what is appropriate in what particular order. If we don't agree to that, for the same reason that if we don't agree that green means go and red means stop, right, there's going to be problems. Right? We need consistency. This is the other thing about math that we should appreciate about, but we don't really. All right? It's consistent. All right? It's reliable. All right? As long as everybody agrees to it. All right? And that we have to agree to logic. Probably, if you know the order of operations already, you might be familiar with the acronyms that are used to memorize, right? PEMDAS is one alternative, right? And then a more recent incarnation of this, which is more concise, right, is GEMS, right? P stands for parentheses, which you should do first, right? In place of parentheses, P, they use the word gem as in group, because in fact you could use different symbols to group things. If you have a lot of things encapsulated one inside of another, like Russian dolls, you know, a doll inside a doll inside a doll, it might get a little cumbersome. So often what happens is stylistically we will opt for a bracket instead of just the standard parentheses. It means the same thing, but it's just to distinguish groupings. All right. Anyhow, that's an acronym: exponents, multiplication, division, addition, and subtraction, right? In the case of GEMS, my understanding is that we basically just have exponents, and then this is understood as multiplication and division, and this is addition and subtraction, but they just don't use those initials, all right? Anyhow, this is the order that you should follow things. There's nothing wrong with it, except that one thing that really must be turbocharged, super clear, is what I wrote here at the bottom, all right? Multiplication and division are equally important. And similarly, addition and subtraction are equally important. So unfortunately, because we have these mnemonic devices, an acronym is an example of a mnemonic device as well, we kind of mislead people. They think that, oh, well, M before D, so therefore erroneously, multiplication always before division. Not so, because multiplication and division are equally important. They're opposite concepts of one another, but they're equally important. All right? That's why I like this, what is what I was taught as a kid, and I want to propagate this as well. It is a different type of mnemonic devices. Again, acronyms are mnemonic devices too. It's a little bit more verbal. We use whole words rather than initials, right? To convey the same information, really. I'm going to write it on these 4 lines inside the lines here. All right? It is this. Please excuse my dear Aunt Sally. Is one mnemonic device better than another? No, but they might have different, not entirely, but they might have some practicality one versus another. Specific practicality, all right? Please, as things that are in parentheses or groups, right? Parentheses and groups, brackets if you like, all right? Should always be done first, right? Excuse, as in things that are raised to an exponent. Superscript font, a little bit smaller, a little bit higher up, right? Squaring, cubing, what have you, all right? In theory, although you're probably not going to see this, square root would be something on the same order as an exponent, right? Technically, it would be the exponent of 1/2, right? But you're not going to see that in this class, all right? Anyhow, that's on the same level in terms of importance. Multiplication, my dear, and division, right, is my dear, right? The advantage to having it memorized like so is that you see that these things are on the same step. They're on the same tier. They're equally important, all right? The mnemonic is arranged verbally, right, in English to make English speakers comfortable with reading it, right? It's not dear my, it's my dear, all right? That's the only reason for that arrangement. But if you had a problem that division was on the left side of the multiplication, then you would do the division first, all right, barring some other condition. Anyhow, Aunt Sally is Aunt as in, this is plus, and Sally as in minus, subtraction, all right? Okay, so everything encapsulated must be addressed first, grouped somehow, all right? You're not going to worry about that, all right? In theory, the inside guts of a radical may be thought of as being a grouping, all right? But I don't want to get into it, all right? Second, exponents you're going to see more likely. Third is multiplying or dividing, and addition and subtraction is the thing that you do last, all right? Unless they're in the parentheses, all right? Anyhow, addition and subtraction are on the same tier. Do whichever is on the left. Whichever left. Left. All right? Multiplication and division are equally important. Whichever you do first is whichever on the left. Okay. So now having stated that, let's do some examples and we'll be finished. All right. The other thing I want to encourage you to do, and also to encourage your own students as well, is get them to write. Physically write, right? Typing is great. It's not something that we should not teach people. It's very important, all right? But it's not the here-all, end-all of, education. All right? You need to get them to physically write. This will condition their minds, and it will also build strategy. So, I'm going to do 2 problems like this type. Let's see if I can fit them. I think think I may have to just do them one at a time, so I'm not going to split the board. But here's an example that is multi-operational type of problem. All right, you want to teach them how to think. Linearly, all right? At least when they're doing arithmetic or algebra. All right? They're doing some other form of math, it may be practical to not be so linear. All right, I'm going to opt for multiplication dots, and then this. Okay, this is the problem, all right? This is, to be, again, very technical, this is an expression, which means that we're going to simplify it. In a more practical sense, what does that mean? It means we're going to take something long and complicated and pack it down into one number. It's going to be satisfying for that reason. We're getting an actual number out of all this junk here. All right? Now, which should we do first? We have a couple of options. We have addition that is tucked into a parentheses. We have division, we have multiplication, and then we have a second subtraction problem tucked into parentheses, and outside of that, squaring. So the hard part would be, all right, deciding ultimately what should we actually do. All right, a person could do all of the arithmetic technically correct, but still get the answer wrong because they did it in the wrong order. Right? I hate those things. If you've ever seen in social media, right, there's always one of those memes going around that is kind of insulting, right? They say like, "Oh, Americans are stupid. Look, 10 people can't get this problem right. Ha ha." It's a multi-operational problem, and like 5 people will, well, not 5, but a majority will say it's one solution. And maybe a minority, perhaps, or some other group of people will say, no, it's this other solution. And it's like, no, you can't figure this out. No, we can if we follow the rules, right? Because math is not debatable, right? There's a certain order, right? And people may make an innocent mistake. We don't reproach them for that. Don't get mad at somebody for making a mistake, but don't celebrate the so-called impossibility of the problem. There's no such thing. Not in a case like this, all right? It's all nonsense, all right? Don't believe those memes, all right? If we follow the order of operations correctly, our focus right off the bat should be the parentheses. So, where are we going to look? We're going to look at the one of two parentheses. We have this grouping and we have that grouping. Which one is on the left? This one. So we have to do that one first, all right? I like to draw little arrows here. I'm going to write basically an algorithm is what you would call this thought process. This is what I'm getting at when I say, make them right, all right? Never yell at a kid and tell them, hey, you should do this in your head, all right? Because you not only will you're putting them down in a way, and that's going to turn them off, and then they're not going to listen to you, all right? You'll do damage, all right? Hopefully not irreparably. But you're teaching them a bad habit. There are some things, rote facts, that you should memorize, like how to spell breakfast, B-R-E-A-K-F-A-S-T, all right? And multiplication tables, all right? Because they're just practical. They make you more strategic when you already know something that is not too complicated. But when it's for something that's more complicated, aside from it being maybe impressive that you could do this in your head, it's needless, all right? You're not competing with other people. You're competing with yourself. All right? Like when you go to the gym, all right, you do some kind of exercise, don't compete with the other schleps that are there, all right? You need to do work for you, all right? Don't compete with other people, compete with yourself, all right? So, you add these two things, all right? And what do you get? 64. I'm just, since I've shrunk this now down to the number 64, I'm going to, crazy as it might seem, write that with the one alteration that has occurred, and then all the junk that remains next to it. When I teach this to people, especially for the first time, they usually resist me. I don't want to encourage that behavior, all right? Because they go, it over and over again. Because it catches a mistake. If you're a teacher and you make the answer keys, you're not allowed to make a mistake, right? If you do, so be it. I make mistakes all the time. But you don't want to. You need to be strategic. And how do you do that? You write things over and over again, all right? You're careful. Teach people to be careful, all right? Now, what's the next thing? That's down to one content, right? Which means in theory, you can ditch this. There's no signs adjacent to it or whatever. This is superfluous at this point. but then your focus must naturally be to the inside guts of this, all right? And now your focus is over here, all right? Write that alteration, right? It's going to be 64 divided by 8 times rather. I'm going to put the parentheses here because temporarily, all right? This is 13 minus 15, all right? We just got through the integer rules. Tidy it up if you need to. It's not written, but this is a positive. So that's one sign. And this is 15 adjacent to it. That's the other type. One of each says that you subtract them. So that would establish a digit of, right, 2. Right? What is the sign going to be? The sign of the larger magnitude. So this is in fact negative 2. Okay? What's still floating around on the outside? That 2 there. Okay, now analyze what you have. You have 64 divided by 8, a division and a multiplication, and then exponents. Exponents are higher up the list. They're the more sophisticated form of multiplication. If you think about it this way, when you come to school, the expectation, right or wrongly, is that you kind of know how to count on your hands, right? And then they teach you a more sophisticated form of counting, which is adding. It's counting with symbols. It's more efficient than just using your fingers. And then a little bit further later, they teach you, subtracting. It's opposite, right? Then they teach you a slightly more sophisticated form of adding, which is multiplying. And it's opposite, division. And then they teach you around junior high, middle school, they'll teach you exponents, which is, again, a slightly more sophisticated form of multiplying. It's multiplying in an efficient way. All right? Anyhow, this is where we are at. Amped up multiplication or regular or division. Our focus has to be here. Right? Look here. So we're going to, again, write that one alteration. Right? It's 64. You don't have to use colors. I'm just trying to make it more obvious what I'm thinking about. Times, what is this really? This is going to be negative 2 times its clone, right? Because it's, 2 iterations. So it's negative 2 times negative 2. Negative 2 times negative 2 is going to be positive 4. So I'm just for a moment, I'm going to put the parentheses here, and I'm going to put positive 4 as the outcome, right? The only reason that I did that is because maybe in certain scenarios you might get a negative. So you got to be careful, right? Anyhow, once you analyze that this is in fact the positive, this is superfluous, and even the positive itself is superfluous. It's unnecessary. It's not wrong to write it, all right? But it's unnecessary. So you have 64 divided by 8 times 4, essentially. Okay, now, here's where people make a mistake, all right? Really. They go, because they know PEMDAS, they'll go, well, M is before D, so therefore multiplication before division, and their focus will be here rather than in these two, all right? Remember, they're equally important concepts. They're on the same tier, all right? All right, so your focus is really here, all right? What's 64 divided by 8? Right. It's 8 again. So I'm running out of space, so I'm just going to squeak this in here. Forgive me. All right, 64 divided by 8 is 8. There's a times 4 left over, all right? And now there is no other choice. You have nothing else to do but just that. So what do you get as a result of doing this? You get 32. And that's the answer. Now again, a little kid is going to fight with you, all right? A kid in middle school especially, all right? They're going to fight with you and go, this crap, all right? You have to, as the adult in the room, never be emotional. I know I said a bad example, right? All right? In other words, don't lose your cool, all right? When they say the same thing to you, when they resist you, when you tell them to write something, you have to go, well, there's a reason, and then you explain the reason to them. And then when they say it again, you go, well, there's a reason, and then you explain the reason to them. And you'll keep explaining the reason like a saint, all right? Until they give up. Your will has to be stronger than theirs. They're only children. You're an adult, all right? And you have to set an example. Patience. Cultivate patience. It's the ultimate skill, all right? Math requires it. This step-by-step thought process might seem like unnecessary tedium, all right? But it's imperative What you're teaching a kid, beknownst or unbeknownst to them or even you, right, is how to think logically. This is a mental exercise in how to think logically, right? The process itself is referred to as writing an algorithm, which has nothing to do with Al Gore, incidentally, right? Waka waka, all right? You want to cultivate that kind of mind in a little kid, right? Because this is the kind of thing that once you have established a set of rules, they're never going to change, all right? And they can do it. They don't believe that. We're, as Americans, unfortunately, we're conditioned all the time. Culturally, they go, oh, this is not for me, I'm stupid. You're not, all right? This is your inheritance. Yes, you're capable of doing this too, but we have to make sure that you rigidly conform to something. Americans don't like to be rigid, right? They want their freedom all the time. That's great for social economic things, all right? But when it comes to education, in your math especially, you have to conform, all right? Don't be American at that point. Be better. Right? Our culture is very important. Our freedoms are very important. And I'm sorry I'm going off on a tangent like this and being hostile. All right? But that's the fault in American culture. That everything is willy-nilly. All right? Not thinking. Not math. Math teaches you how to think straight. Right? And it's a very important skill. How to be a poet is a very important skill. How to be an artist and an athlete is a very important skill. One is not more important than the other. I'm not saying that. I'm just telling you to navigate this plane of existence, real ordinary life, you have to cultivate multiple ways of multiple perspectives. And this is not less important than that. This is very, very practical. Be better and teach better. All right? Here's one more. What if you get a situation like this? You're probably less likely. But if it comes up, I want you to be prepared. Because it's the only time that I would say that it might seem to deviate from the set of rules. Right? Sorry, this one's involved here. I'm going to write it carefully not to make a mistake. Right? You could see that this has a lot to it. Right? When you get more comfortable, and that is the goal, comfort, right? You will not have to, stress about things, right? You'll be conditioned to just look at things automatically, right? Anyhow, let's go through this step by step. This is an example of something that's not just an expression. I'm going to put a little thought cloud here. The thing that we had before is an expression. This is a certain type of expression. This is known as a rational expression. And there is one little caveat. Right? When you have a rational expression, you're going to follow the same order of operations. But there's one operation hidden in here. And it's this one that I'm highlighting in red. Right? The red line is really division. Do that last. That particular division do last. If it is possible. There are times when it's not possible or it's not really practical. All right? What I'm getting at is this. You're going to do all the top according to the order of operations, and then you're going to do all of the bottom according to the order of operations, and then, if it is practical, and you can only make that decision at the time, do this line last, because that's really dividing. Okay? All right, so here we have our choices. We have some minus out here, which, since it's free floating, for right now, just put it here. All right, it's not really going to be affected while you're doing this work. You can put it here if you want to. I wouldn't even worry about it. All right, until I get it narrowed down to one figure, ignore this. All right, Then you have things that are encapsulated in brackets. Again, they're the same thing as parentheses. It's just trying to make it visually easier to distinguish one grouping from another. So you have minus, and then you have the subtraction of some sort, right? And then you have the subtraction encapsulated, the innermost, it's not proper speaking, sorry. The innermost parentheses, right? We're going to do this first. Do innermost parentheses first, right? Then we'll square, then we'll subtract. All right, so I'm going to try to keep everything that I do that is just the top, all right, in blue here, all right? And I'm going to replicate, as I suggested before, little alterations slowly but surely. Do write the same thing over and over again. I know kids are going to fight with you. It may not be your own inclination either, but just give it a chance, all right? You will not get stronger unless you feel resistance a little bit, all right? So, 4, all right, is in this encapsulation. We're ignoring that. We're going to narrow down what is in parentheses here, all right? 6 minus 12 is really positive 6. And minus 12, that's one of each. You subtract them. That establishes the magnitude of the digit as being 6. The sign of it will be the bigger magnitude, so this is negative 6. I'm still keeping the parentheses that are there. And this is still squared, and that's still closed. All right? Next line. All right? I have my choice between squaring something and subtracting something. This is, again, an amped up form of multiplication, and this is really just subtraction, all right? So what do I really have to do? I have to do this now, right? 2 iterations of the entire kit and caboodle, the sign and the digit. 2 clones of this, all right? Negative 6 times negative 6. So this is negative 4, all right? Minus, I'm just going to encapsulate this temporarily. Let's see. Positive 36 is the outcome. All right. Now, when you get to a situation like this, right, where you just have 4 minus a positive, this is superfluous. Remember that math people, for better or for worse, and in this case it would be for the worse, all right? They leave out information, all right? They leave out positive signs when it's a convenience. They leave out decimal points, zeros, and ones. In this case, this positive is the outcome of negative 6 times negative 6, which is the only reason why I wrote it. But from this moment forward, just like this parentheses is superfluous and unnecessary because it's just one content, really, that symbol is also unnecessary, all right? Which means that you have this now. You have negative 4 minus 36, right? That is, in essence, what's left over. Now, I would fill in the same information here for 4. If it's not written what you assume it is, it's a positive 4. This is only so I can conform to the rules that I have established for signs. All right, positive 4, negative 36. All right, positive 4, there's a 1 of each, so you're going to actually subtract these, which means that's going to be a what overall, all right? Well, let's do the sign first. I'm getting ahead of myself. If you have 1 of each, you subtract, which means that that's 32, right? All right, what is the sign going to be? It takes the sign of the bigger thing. So I'm just going to borrow the little encapsulation here. And I really should, as I promised myself, I would continue to write in blue. All right, that's negative 32, all right? That's the top completely narrowed down, right? If you want at this point, and it's entirely your choice, really. The negative that has been going along for the ride all to this point, as I mentioned before, you could either tack it to the bottom, all right, or intuitively tack it to the top, all right? I would do that, all right, just to get in the habit so I never have to worry about it again. Automatically gravitate this to here, all right? That means that the bottom is automatically positive because it's one or the other, not both simultaneous. Wait, sorry, I don't know why I'm having my coffee repeat on me. It's all the hostility from math, all right, is what it is. Anyway, if you have this now narrowed down to one content, again, these brackets are superfluous. They're not necessary. But what do you end up with? A double negative. All right, so what is a double negative? It's a positive 32. That's above the line. That's crunched the whole top. All right. Now, the bottom, I'm going to try to do essentially the same thing adjacent to it here for the sake of not erasing. Because sometimes if you erase something, you're obscuring. All right. And I only have this board, so I have no choice sometimes. But like if you have a full-size classroom, and ideally that's what the future will be, all right, don't erase things. Sometimes you want to see the entire forest all at once. All right, so anyhow, you have this that is in black down here, below the red line. So inside the bracket, you see division, addition, outside immediately is squaring, subtraction, and then apparently a stylized form of dividing here as well. Where should your focus be automatically? It should be at the bracket, all right, the group. And inside the bracket, you have your choices between dividing and regular ordinary adding, which is really more important in this case, these two things, all right? So over here, I'm going to write them with their slight alterations. There's the bracket, all right? 9 divided by 3, which is 3. There's a plus 4 left over inside. There's a square, and there's this minus 34 divided by 2. Is it wrong to try to straighten out other things that you can legally get away with? No. But when you're a teacher, you have to rigidly conform to something to A, set a better example, and make sure that you don't make a mistake. Because again, you are the person who makes the answer keys, right? So if you make a mistake, it's much more serious than if a kid makes a mistake. You have to make sure, at least put forth the effort, right? Not, beat yourself to death over it, all right? But do make sure you avoid mistakes if you can help it, right? Then people will take you less seriously if you do that, all right? Oh, believe me, I do. You'll be like, this guy's teaching you about bananas and apples and ones, and somehow that's a coordinate. All right, not because I want to, just because the situation arises for it. All right, anyhow, I do love math. All right, it's my religion. All right, anyhow, 9 plus 4 is what's left behind. All right, and this is squaring, and again, this is minus. What should you do? Well, you're still encapsulated here, and it was the second operation, namely plus. There's no real signs to worry about in this case, so just deal with this stuff that is technically below the line here, all right, and continue, right? Next line of logic. This is 7, naturally, when you add 3 plus 4. You could, if you want to, you could say, well, they're both the same signs, so add them, but it is intuitive also. It's 3 plus 4. Squared minus 34 over 2. Someone is texting me for whatever reason. All right. Now, I have the choice between squaring, amped up version of multiplication, minus subtraction, or this stylized form of division, if you will. Squaring is exponents. They're higher order than ordinary division. So my focus is still here, below this line, all right? What do you get when you make clones of 7, 2 clones, and multiply? You get 49, all right? All right, I'm going to leave this here for a moment. I could just decide as an afterthought later if it's necessary. This is what's left over, all right? Now, if I have to choose between regular subtraction and apparently this is dividing, all right, what should I do? Well, division is for sure higher order than subtraction. So I really should straighten this out at this point, all right? Anyhow, what do you get? I'm a little short on board space, so what I'm going to do is kind of draw on top of it for a moment, all right? Focusing here, 34 divided by 2 is asking you what's half of 34. Well, 2 goes into that 1 time with 1 left over, and 2 goes into 14 7 times. So it's 17 is the overall outcome of doing this, all right? Now, that means that realistically, this is superfluous. I can get rid of it now. It's 49 minus 17, which is pretty much intuitive, right? What is 9 divided, pardon me, what is 9 minus 7? It's 2, right? What is 4 minus 1? It's 3. That means that after all of this trouble, right, and we're going to do the line portion of the show here, after all of our trouble, we had positive 32 above the line, all right? And this should be a red 32 here. And it's just a positive the way it would work out as well. All right? And there's this line in between that. Again, we do that last. That particular division, because it's a fraction, we do that last. All right? So what's something divided by itself? 1. What's a positive divided by a positive? Positive. All right? You will find that happen a lot, right? Where you have something, sorry, I'm dropping stuff, that is exceptionally complicated, right? It's involved, as you can see, it looks like a lot of scribble if you didn't follow it along, all right? But when you stick it through, it ends up with something that is elegant and simple, 1, right? And upper level math, we used to try to not get yelled at, you know, by our professor, right? It's an ultimate bad example, right? And, you know, brilliant man, he would explain something, and it would take like an hour and a half, and then he would turn around and ask a question, and he would go out to check and see if people were paying attention. And he'd say, like, so what's your answer? And we'd be like, guessing, because we'd noticed after a while, well, the answer was either 1 or 0 or E, you know, because it was calculus. Anyhow, so he had a 33 1/3% chance of not getting yelled at if you guessed one of those 2 things randomly. Anyhow, you don't have to guess, all right? And nobody should yell at you, really, all right? Don't yell at your students, all right? You'll be sorry if you do, all right? It turns people off. All right, you could be passionate about something, all right, which is what I feel, all right, and I'm sorry if I am setting a bad example, all right, but you could be passionate about something, but in a constructive way, all right, all right, don't be a monster, all right, especially as a male teacher, all right, you don't want to be scary, all right, anyhow, we are finished, all right, thank you for sticking with me all this while. I know that this is arduous, all right. Do this, all right, for homework, all right. We've just covered section 5.2, so do 5.2 in my lab, and if you've done that, you're basically good to go, all right. All right, next week there'll be section 5.3 in 2 parts, so that might be a longer video. I'm sorry, I apologize for that ahead of time. It'll be in the homework. You'll see section 5.3 part 1. And section 5.3 part 2, all right, because it's going to involve fractions, so we have to take our time with that. Okay, thank you very much for listening and for sticking with me. All right, be careful out there.